Hey gang, welcome back to Biostat. We're going to finish up our discussion on the different type of chi-squared tests that we can run for categorical data. Today we're going to concentrate on the chi-squared test of independence and one called the chi-squared test of homogeneity. Basically these are not that different from the one we ran in the previous lecture, the chi-square goodness of fit. The chi-square goodness of fit is a test to see, again, just as a reminder, is a test that we use when we want to see if the data we collected, the categorical counts we've collected out in the field, match up to a prescribed or predetermined set of probabilities or a genetic theory, like in that one particular instance. And so that one, we only needed one categorical variable, and we can break that down into subcategories and get counts, and then we can look at that compared to a predetermined set of probabilities. The chi-square test of independence and homogeneity work off of two different categorical variables being broken down, but while they're very similar, these two tests are very similar in a lot of ways, what we use them to determine is a little bit different. So let's get into them a little bit here and discuss what goes on with them. So we'll spend most of the time here at the beginning talking about the test of independence. The chi-square test of independence, we sometimes call that the chi-square test of association. And so sometimes you'll see the word association in place of independence. They basically mean the same thing though, but we're using this test to assess if whether the perceived dependence in sample data may be a fluke. In other words, is the result of our two categorical variables we're looking at, or is it a result of are they really, we're trying to see if they're dependent or independent. The definition's kind of like skewed here, but that's really what we're looking for. Are the two variables, categorical variables we're interested in, do they depend on one another, or are they independent? The test takes a sample from a single population, so we go out and collect this whole population, and we divide it up using the two categorical variables that are usually predetermined by us, the researcher. These two categorical variables are random and can be broken down like we did with the chi-square goodness of fit test into subcategories. So like when we did the flower example, the colors of the different snapdragons, we had them broken down in the color variants. So the categorical variable in that case was color, but then we had the colors as subcategories. Both categorical variables in this case are random, and the randomness in this case refers to the fact that our categorical variables represent that we do not, as the researcher, do not assign the participants in these subcategories. All right, so it's not like we went out and purposely collected people from different groups to fit in these things. We've went out and grabbed a whole group of people, and then we looked at them closer, and they fit into one of our subcategories, and they get counted in those areas. And they should only be counted in one of those subcategories for what we call the row category and the column category. We'll see that here in a minute when we look at what we call a contingency table. Not sure if I mentioned what our tables we look at with these, but we call them contingency tables. All right, so contingency tables. Okay. But what the chi-square test independence does with the contingency tables is that we have counts in each one of the little cells, all right, that represent what our data. So the counts in one subset, like say in one row, for example, it's comparing that to the counts in other rows within the data. And so that's how it's comparing back and forth here. This test has a very limited but an important purpose. This test only, emphasize the word only, assesses whether the data indicate a statistically significant relation among our various categories. All right, so it really just measures, are these two categorical variables dependent, or are they independent? That's all it tells us. It does not measure how strong the apparent relationship might be, or tell us, more in-depth details than that. It's just simply, are these things dependent? Are they not independent? Because if they depend on each other, maybe we want to look at why that dependency causes, but that would require us to do other tests or other further research. But if they're independent, it means they don't really affect one another. This is kind of like the categorical data's version of the correlation we talked about earlier in the semester. Correlation does so with looks at the relationship with quantitative data, and it's mainly used in what we call regression to see how two variables relate to one another. So this is similar to that in an aspect, except for we're not going to get a correlation coefficient value for this to tell us how strong that relationship might be. So that we don't get from this. We just know that there is or is not a relationship. Some examples of tests of independence that we could do would be age versus the severity of some kind of disease. We'll specifically look at an example of that today, where the age can be broken down into subcategories of different age groups, and the severity of the disease can be given its own definition, like it's like very severe, moderate, non-existent, things like that. One example I use from grad school in a couple of classes is drinking frequency versus the criminal offenses that someone might have. So you get a single population from, say, a big college or university like UGA or something like that, and you find out about the students that you sampled. How often do you drink, and you get subcategories for that, and have you ever been arrested for anything, and what that arrest might be. So you could categorize that, so you could see is drinking necessarily dependent on the kind of criminal offense it is, and it may or may not be. Another one that some organizations might do would be desirability level of hiring a new college graduate. All right, because some places like to hire brand new college graduates, and sometimes they'll base that on the type of school they go to. So like, oh, we hired a Harvard graduate, versus, oh, we hired an MGA student. But the employer's rating of said employee, because as we'll find out, oftentimes that how an employer might rate an employee may be very different from where they went to school. Just because you went to Harvard doesn't mean you're going to be an automatically great employee. And just because you went to MGA doesn't mean you're going to be a subpar employee. You might be one of the greatest they've ever had. So that's the kind of thing that you might be able to look at to see if it's dependent, if the hiring rates are dependent upon that, or if hiring in some way is dependent upon those two things. The assumptions for this test are very similar to our goodness of fit test as well, except that all expected values must be at least 1. We don't really want very many of those. And no more than 20% of the expected values those counts can be less than 5. So if you have 5 cells or 6 cells in your, let's say we had 6 cells, 3 in each row in our table, we wouldn't want any more than maybe one of those to be less than 5. And we can't have any be 0, is what that first comment is really making. You don't want any expected values to ever come out to be 0. That would be bad. And so really what you really still want to do is hopefully most of them come out to be greater than 5, and that will be a plus. We can continue on with our test and our assumptions in this case. The same thing goes for the test we'll do later, the homogeneity test. So let's talk a little bit about how this is done by hand a little bit. I'm going to do one example today of this by hand, but it gets repetitive because it's the same procedure for any of the independence tests or homogeneity tests. But the differences here will be how the hypotheses are stated. So for a test of independence, aka association, all right, you can use those words interchangeably. The HO here, the null hypothesis, is that the row and the column variables, like say that was the age of a patient and their disease type would be the 2 row and column variables, are independent, or the alternative would be that those 2 things are dependent or aka not independent, but dependent. And so if you use the words association here, then here you would say that they're not associated, because if you're independent, you're not associated. And if you're dependent, you are associated. All right. So to estimate the expected values of each cell in the tables we'll be looking at, what you would do by hand, you would define the E sub ij, and what that represents is if you've got say a certain number of rows and columns. Say we had four columns and 2 rows. Then you would take, and you had the total of the rows here and here, and then the total for the columns here, here, and here. This formula says if you want to find the guy in the I sub j row, the ij represents, for example, if you were in cell 1-1, you'd be right here. And if you wanted to find that, you'd take its row total times its column total and divide it by the grand total, which would be of all participants. And that would get you the value for E sub 1-1. And then to find E sub 1-2, you would take that row total times its column total times the grand total. And you just keep going down the line like that. That's all that formula means. Once you have all those expected values, to find compute your chi-square test statistic by hand, you would take for each one of those cells and you would calculate the following thing. And so you take your observed values minus, and this should be a j here, your expected value. This is very similar to the formula we used with the chi-square goodness of fit test, by the way. Subtract them, square it, and then divide by the expected value of that cell as well. All right, and you'd get all those for every cell, and then you would add them all up together to get sum them all up to get your chi-square test statistic. The p-value, if you were going to do this by hand, would be to use the p chi-squared function here to get the p-value for your chi-square. So p chi-square. You put in your chi-square value we calculated in part 3, the degrees of freedom, and lower dot tail equals false. Here the degrees of freedom equals your row minus 1 times your column minus 1. So for example, if your rows equaled 4 and your columns equaled 2, then your degrees of freedom would be 4 minus 1 times 2 minus 1, and so that would be 3. I should put equals there. 3 times 2 minus 1 is 1, so you end up getting a degrees of freedom of 3. So that's what you would use in that case. Okay. So it just depends on the way the table and your data is built out, how many rows and columns you have, how many subcategories you have in your rows and your columns. Okay. And so without further ado, let's get into doing one of these. We're going to do this first one by hand, and the rest we'll do all in R. So the Centers of Disease Control and Prevention wants to determine if the severity of a skin disease is related to the age of the patient. Suppose that a patient's skin disease is classified as moderate. So here are classifications of the skin disease severity. Either it's moderate, mildly severe, or severe. The patients are divided into 4 age categories. They didn't give us the specifics on that, so we just know there's 4 different age categories. And the table below shows the data. Can you conclude that the severity of the skin disease is associated, all right, in other words, dependent upon the age of the patient? All right. Well, let's see if we can conclude that. So notice my table here. The numbers in blue are the ones that are important to me, and everything else that's in black, the numbers in black are all the totals, the rows and the column totals. So there are my 4. It's categorical variable 1 is the age, and it's broken down into 4 subcategories, and the row category row category is called severity, and it's broken down into 3. So this is what I would call this. All tables are called defined as row times column, or row by column, if you will. So it's gonna, this one's a 3 by 4 table, if you will. You kind of ignore the totals when you figure this out. All right, that'll become more important when we do it in R. We'll need to know that. Okay, so got all that information. So we need to construct our first step in any of these tests. We know we want to show that, or we want to see if we can conclude that the severity of the skin disease is associated to the age of the patient. All right, so we're looking to see if age and severity are either independent or dependent. All right, and so the null hypothesis here is the severity of a skin disease, because we don't know what type this is either. They didn't tell us that. The severity of the skin disease is independent of age. All right, and then the Ha here would be the severity of a skin disease. And age are dependent. Now you could have worded these a little bit differently if you used the words not associated in the Ho and associated in the Ha. You might say something in the Ho like the severity of a skin disease and age are not associated, and in the Ha you might say the severity of a skin disease and age are associated. So you can use whichever one of those you're comfortable with. All right, so we need to calculate the expected values and make sure they meet that assumption that they're all at least 1, and no more than 20% of them are less than 5. So we're hoping they're all greater than 5. So here's how we calculate each one. Here's the formula for each one. So if I start in the first row, we call E11. This is E11. If I want to find the expected value of that E11, that's going to be equal to the row total times the column total, all divided by the grand total of 216. All these will be divided by 216. Okay, and when I do that in my calculator, I end up getting 7.78. I'm just going to erase this here. 7.78. E12, so first row, second column, is equal to its row total, 70, times its column total, 81. So 70 times 81 is in the top, divided by 216. And if I throw that in my calculator, I got 26.25. And we'll just calculate the first row outright and not worry about I'll just give you the values for the second and third rows. E13 would be equal to the row total again times its column total. So 70 times 66 over 216. And E13 is equal to 21.39. And lastly, for the fourth E14, first row, fourth column, we take the row total of it, 70 again, times its column total, 45, and divide it by 216. And when I do that, I get 14.58. All right, I think you're kind of probably getting the idea of what I'm doing here at this point. To do the second row, I'm still going to use 216 as my denominator, but E21, second row, first column, I would do its row total, 78, times 24, divided by 216. I will stop calculating them after that and just give you the rest of them, I promise. So when I got that, I got 8.67. So going further, the rest of them are in order. E22 is equal to 29.25 when you calculate it. E23 is equal to 23.83. E24 is equal to 16.25. And then E31 is equal to 7.56. E32 is equal to 25.50. E33 is equal to 20.78. And lastly, E34, row 3, column 4, is equal to 14.17. Well, looking through those values, I don't see that any of them are less than 5. All of them are bigger than 5, as a matter of fact. So we're good to go. Our chi-square test should be okay. We've met that assumption. We know the data was randomly pulled from population, and this checks out, so we're pretty good to go. All right. So the next thing up is we have to calculate the test statistic. The formula for that, remember, is we have to sum the observed values from the each cell, the observed value we saw in blue minus the expected value of that cell. All right, we square that and we divide it by the expected value of that cell. So we'd have to get that for all 9 cells and add them together. That's what that formula stands for. And if I go back here and take a look, the first one will be 15 is the observed value, and the E11 is our expected value, so 15 minus 7.78. Square that and divide it by 7.78. All right, so the expected value. Then we go to the second one and we go, okay, what was that one? 32 is the expected value there, minus 26.25. Square that and divide it by its expected value, which was 26.25, and we just keep going through the whole thing. I'm not going to bore you with going through all that, so dot dot dot. We end up getting, in the end, when we calculate it by hand, we get the value of 27.14675. Okay, so that's what we need for the next step when we find our p-value. We want to find the probability of getting that event or higher. Okay, so remember, this formula down here was p chi-squared, and we put in the chi-square value we got, the degrees of freedom, and the command or the argument lower dot tail equals false. All right, so we know the chi-square value already is 27.14675, comma, we need the degrees of freedom. We'll plug that in just a second. Lower dot tail equals false. So remember the formula for the degrees of freedom, we gave it a few slides ago, was the rows minus 1 times the columns minus 1. So how many rows did we have and how many columns did we have? So looking at just the blue, the number of rows we had these 3 rows here. We don't count the total, so we had 3 rows, and we had 4 age categories, so we have 4 columns. So this is a 3 by 4 matrix, so row by column, right? So we know to plug in here, we got 3 minus 1 times 4 minus 1, which is just 2 times 3, which is 6. So our degrees of freedom in this case are 6. So we plug that in here and throw it into R real quick, and let's see what we get. So for that value there, it's p chi-square. I'm just going to copy and paste it from my notes. Again, I will always have these in your R code only notes. I know I say that every time, but I like to keep that up. And there we go. We get something about 0.00014. That's a pretty small p-value. We're definitely rejecting the null hypothesis here. Okay. And so what would we conclude? That's small enough to reject. We would conclude, since p is less than 0.001, we reject ho. There is very strong evidence that the severity of a skin disease and age are dependent. All right, so keep in mind, all I did here, again, just like we did with every other conclusion we've written for hypothesis test, I wrote there is very strong, you know, since we rejected, there is very strong, or if the p-value had been a little bit bigger, we might have said that there was strong evidence. And then we state the actual alternate hypothesis that we stated originally right here. So we just restate that in there. If we had no evidence that this was true, then we'd say there was no evidence that the severity of a skin disease and age are dependent. Therefore, that implies that they are independent. Okay, or that we couldn't prove that they were independent. So that's that. So let's do another one of these, but let's do it in R. I have the way to do this one in R in the R code only notes. So if you want to see what I did there, there's an example of it right below the steps for this example that will get you all the things you need. We're going to walk through it here piece by piece. Actually, let's do it real quick anyway. What the heck? We've got time. So to get this into R, I have to first construct a matrix to get my data into R. This is not going to be a nifty little table that we can automatically just upload into R and all that good stuff. We have to upload this in as a matrix. So you have to give your matrix a name. You can call it whatever you want. I usually try to call it something like, in this case, skin mat for skin matrix. You can be as silly with your names as you want, or as simple with your names as you want. Inside the matrix command, all right, we're going to set it equal to into matrix. We have to do C. We have to create a vector in there. This vector is going to be what I'm going to enter in. As a matter of fact, we'll just do this. Let's pull this over here a little bit so we can see that, and then we can see the table a little bit. I'm going to go back to the original table. The numbers I have in blue here on the table, I'm going to start listing them going left to right, row by row. So I'll go 15, 32, 18, 5, 8, 29, 23, 18, 1, 20, 25, 20, in that order. So we enter them in, and of course we separate them by commas, just like we've done when we've made other vectors in R. And just keep putting them in the way you see them row by row. 18, 1, 20, 25, and 22. Double check your data before you move on, because it's easy to make mistakes. 15, 32, 18, 5, 8, 29, 23, 18, 1, 20, 25, 22. I'm good to go. The next thing you have to put in this is, remember, this is a 3-row by 4-column matrix. And so since we said there were 3 columns, 4 rows here, we have to tell R that as well. So right after that, we put after the vector we created, we put a comma and we do 3, 4. And then after that we do comma, and we tell it by row equals true. So we told it the size we wanted. We told it to put those numbers, fill the matrix by the row. That's how we entered them in. And we hit enter. And if I check that skin mat real quick, type that word in there and check it, that should look just like the stuff in blue I have down there. If you've got that, then you're good to go. All right. The next thing we can check is our expected values, just like we did by hand, except for it's a heck of a lot quicker here. We call forth the chi-square.test function, put our matrix in there, skin mat, and after it put the money symbol and then the word expected, and this will just spit out a matrix of the expected values for us, and these should match up very closely to what we got when we did it by hand. So if I move over here to where we did it by hand, 7.78, 26.25, 21.39. They didn't round theirs off as short as we did, but so there will be a little bit of difference probably in their chi-square value that they got versus ours, but that's okay. It'll be close enough for us in the long run. And everything else looks the same as well, so it matches up nicely. But you can see how much quicker it is to do it here than it is by hand. And then to run the chi-square test, we call back the chi-square.test with the skin mat inside the parentheses and erase the expected value of money symbol and run that, and there's our p-value, which is again roughly about 0.00013, and the chi-square value they got was 27.135. Well, notice there's going to be a little bit of difference in theirs versus ours. We got 27.146 versus their 135. Theirs is more accurate because they went to more decimal places with the expected values, and so this is going to be a smidge smaller than ours, but we got the same p-value regardless because the difference between 27.146 and 135 is not drastic enough to cause the probability to be that different. Okay, so that's kind of cool. So it's a lot quicker obviously to run it by this way. So the rest of them will run this way. Okay. So example 2, let's do one more independence test. So in a clinical trial of effectiveness of echinacea for preventing colds, the results in the table below were obtained. All right, so they went out and got 207 people, and you may be looking at this first and going, wait a minute, especially those of you who have read enough research stuff and go, there's people on a placebo, some on an echinacea 20% extract, and some that were given echinacea 60% extract. Well, wouldn't that clarify that the researcher forced people into those things? Well, not necessarily, because you can keep that random as well. The researcher can randomly assign these things to people, and that keeps the randomness there and keeps it from hand picking who you gave the placebos echinacea, so it still keeps it random. So these still are 2 random events here. They just grabbed 207 people and somehow randomly assigned them these different doses of treatment, and then checked after a little while to see if they got a cold or not. So we're going to test the claim that getting a cold is independent of the treatment group. So the word claim has been thrown around a little bit here. The claim in statistics does not always have to be the ha. A lot of books will kind of lead you to believe that the alternative hypothesis is what the researcher is claiming, but sometimes the researcher's claim is actually the null hypothesis. They don't want to prove otherwise. They want it to stay in, they want these things to be independent, that they don't have an effect on each other. So really the claim can go either place, but you're always, whenever you write a conclusion or for your hypotheses, you always state it in terms of the alternate hypothesis, regardless of what the claim happens to be. Okay, so don't let that trip you up if that's something you saw in this or thought about. Okay, so let's take a look at our table real quick. We've got 103 people were on the placebo. 88 of those got a cold. 52 of them were on the Echinacea 20%, and 48 of those got a cold. And Echinacea 60% extract, 52 folks were on that, and 42 of those folks got a cold. So apparently this doesn't look like it really made a big difference here, does it? So we've got 2 rows and 3 columns. And so this is a 2 by 3. We'll need to know that when we go to enter things into R. Okay. So let's get into running the test. So step 1, as usual, we state our null and alternate hypotheses. And here it's the HO is getting a cold is independent of treatment versus the HA where it's getting a cold and treatment are dependent. Okay. To get the contingency table into R, I called mine ECMAT. I'm going to run through it by hand real quick instead of just looking at it on the screen there. Clear that out real fast. ECMAT, not a ECMAT, ECMAT, Echinacea matrix. I will tell you, I had dated a girl for a long time back, many moons ago, whose mother was very much into Echinacea, and I never found that it helped me with much. So I still got colds and stuff like that. So we need to put that data in as we saw it. Let's pull that table. Let's pull this table back up. Actually, we can cheat right here. We use this right here because that's the data in the table. The stuff I highlighted in blue, not the totals. We never put in the row and column totals. So I've got 88, 48, 42, 15, 4, and 10. So 88, 48, 42, 15, 4, and 10. So we're good to go there. Come out of that vector that we created, comma. This was a 2 by 3. So 2, 3, and we put a comma and then by row equals true. Let's make sure our ECMAT is going to match up to the ECMAT we have on my slide. And it looks like it will. And it does. So we're good to go there. We can check the expected values in step 3, which is something we always should do. So again, that's chi-square.test. In there we need to put our matrix that we created, and then the money expected. So we're looking at expected values only, and there they are. None of them are less than 5. Again, we're good to go. We're happy about that, and the next step would be for us to run our hypothesis test, which is on the next slide. So if I move that over just a smidge more, there we go. So again, I can call that back up by pushing the up arrow once and erasing the money expected, and boom. We get a pretty big p-value of 0.2316. So it looks like this person that was doing the test, their claim was correct. So our conclusion there would be that since p is greater than 0.10, we do not reject the HO. There is no significant evidence that getting a cold in treatment is dependent, aka they must be independent, or something else. We don't have enough proof to prove that they're dependent. So they're independent of each other. So apparently Echinacea doesn't really have much of an effect on helping with colds, is what my final say-so would be there. There's not a lot of strong evidence there, because there needs to be a little bit more to that test than that. That's all it told us, was that they're not dependent. All right, so you can get a cold whether you're on Echinacea or not, apparently. Anyway, let's talk about the test of homogeneity next. All right, so put this back in place and come back over here. So the chi-square test of homogeneity and independence are conducted in the same manner. So the way we calculated everything when we calculated the expected values, the chi-square, the p-value, all those things are done exactly the same. There's no difference in the two tests when it comes to that. The difference really lies in the way the sampling is done, the sampling scheme that we do, and the conclusions we draw, which ultimately comes down to also saying that our hypotheses are going to be a little different. We'll talk about those in just a minute. So in our test of independence, we were randomly selecting a single sample in people or items out of a single population, and then we classify those in the units into two categorical variables that are random. Okay. So since both the row and the column categories are random and can be broken into several subcategories, all right, so remember that. What we're looking for there is we're trying to determine if the two categorical variables are related to each other, or aka associated to each other, or aka independent or dependent. In the test of homogeneity, it's a little bit different. One of the categorical variables specifically, then it can be either the row or the column variable. It doesn't matter how you set up your tables. That doesn't really matter here. But one of those categorical variables are assigned by us, the researcher, and it's not random. In other words, we choose how to separate that, and we basically collect a certain number of items or people that fit those descriptions specifically. All right. So in this case, we will consider the subcategories of the assigned variable, the one we are assigning, as different populations. So they're like two different populations. And we are interested in seeing or testing if the population distributions are the same or different. So we will have the other categorical variable will be random. It won't be something in our control, and it will have subcategories just like what we saw with the independence test. But the other category will be something we do know about, and we've made them two different populations, and we're trying to see if they're similar or different somehow. Homogeneity actually means that, as we'll go over here. So in the context of this test, homogeneity just means they have the same distribution. All right. Versus if we were doing a test of what we call heterogeneity, which is, there's not really a test called that one, but heterogeneity would mean they would be different. Okay. The biologists probably know that pretty well. The hypotheses for the test of homogeneity are as follows, though. The Ho will always be the population. It could be the column. It could be column or row, depending on how your table's set up. This is kind of misleading here. It's the population, whatever you're looking into. The distribution of that populations are homogeneous or homogeneous. Tomato, right? And the Ha here is that at least one population distribution is different. All right. So you can have more than two populations in one of your categories, the way it's broken up, but you can't. This only tells you whether they're different or not. It doesn't tell you how they differ. It just tells you that they're different. So very similar to the other test. That's really all this test tells us. Okay, but that's the important part here, is that we're looking to see if the distributions are the same. In other words, they're homogeneous, or at least one of them is different. All right, so they're not all the same. Oop, went too far. So this is a good example from wildlife ecologists. So some wildlife ecologists monitored the breeding habits of a mountain plover, and I had to look this up, what it was, when I first found this example a few years ago. Plover is a medium-sized ground bird. All right, and so they monitored these breeding habitats for 3 years, and made note of the plovers nests. All right. They found nests on agricultural fields, which I call AF, in prairie dog habitats, which we'll call PD for short, and grassland, which we'll just call G. The nesting choices varied across the years. The table below shows the data. Test to see if the population distributions of the nesting locations, all right, so populations of the nesting locations were different over the 3 years. So the 3 years are the things that we as the researcher decided upon, and those are the populations in this case. The nesting locations, actually, I take that back. Now that I think about it again, strike that, reverse it. The population distributions here of the nesting locations are, I wouldn't say that that's truly assignable, because you can't assign where these birds nest. So the population distributions of the nesting locations may differ over the years. So like they're calling the years the population distributions here. So I was correct in my first assumption. I apologize. So yes, the years are really where we're looking at, and looking at the nesting distributions differed from year to year to year. So did this change from year to year to year? That's what we're looking at. The other thing we want to note here is that this is the numbers in blue specifically represent 3 rows and 3 columns here for the years. So this is a 3x3 matrix that we're going to create in R. Okay, so the population distributions, the hoe is going to be that the population distributions of nest locations is the same for the 3 years. So where these birds were nesting remain the same over the 3 years, and the ha is the population distributions of the nest locations are not the same for all 3 years. Okay. We have to get the contingency table into R, and we do it just like my previous example. We have to create a matrix which I called plovemat, and then put in the data as we saw, row from left to right, row to row. And so that's how we would do that. And then we do comma 3 because it was a 3x3 matrix, and then put in our by row equals true, and it should spit that out for us just fine. Won't hurt for us to do this in R real fast. And matter of fact, before I do that, let's slide over so we can see the actual table, because that's what we're working from. And so called up plovemat equals matrix C, and we're going to put in 21, 19, 26, 17, 38, and 12, 5, 6, and 9. And then comma, that was a 3x3 matrix, so we're outside of the vector. Pay attention to that. And then by row equals true. What did I not like that I did? Oh, it's the way I spelled by row. Put BT row. And plovemat should look like our table there: 21, 19, 26, 17, 38, 12, 5, 6, 9. We're good to go. We'll clear that out for a minute. So we need to check the expected values of that next. As you can see in my table that I just did chi-square.test. Put my plovemat name in the parentheses and the money expected after the parentheses, and it spit out my expected values for each one of those cells. And none of those are less than 5. We've got one that's close. If this one had ended up being 4 point something, we would still be okay to go with this test, because that's only one cell out of 9. That's less than 20% of them. So remember, the rule is you can have some of them be less than 5, but you can't have more than 20% of your total cells be that way. But in this case, where you lucked out, we didn't really have to worry about this one because it didn't become lower than 5. So again, we're good to go, and we need to run our chi-square test. So in R, I just want to run this one at least. Chi-square.test and plovemat, and we get a small enough p-value to reject 0.007015. All right, so our p-value is 0.007 roughly, which is definitely in between the 0.001 and 0.01. So we would conclude that since the p-value is between 0.001 and 0.01, we reject the hoe. There is strong evidence that the population distributions of nest location is not the same in all 3 years. Okay. And that's it. So that's really all we can say there. I mean, again, remember, we're restating the alternative hypothesis here. So the fact that we're just saying there is strong evidence that the population distributions of the nest locations is not the same in all 3 years just means we've got reason to believe that something's going on ecologically there in those systems to change for the birds to be changing where they're nesting. There's some things we can conclude from that, but we can't go forth with hardcore proof without maybe doing some further research or analysis as to why that's happening. There may be some other things types of data we could collect to try to find out why that's the case. But here we can't do anything other than say they're not the same all 3 years. Okay. Because that was our ha, right? Let's do one more. This one's a good one too. This one's hospital related. So the head of a surgery department at a university medical center was concerned that surgical residents in training applied unnecessary blood transfusions at a different rate than the more experienced attending physicians. That probably isn't a good thing. So therefore he ordered a study of 49 physicians and 71 residents. So he collected two separate he took samples from both groups of the attending physicians and the residents in training. All right, so there's our categorical variable, surgeon type, I guess is what we could call this. Not really type, but there's probably a better wording for it. So for each of the 120 surgeons, the number of blood transfusions prescribed unnecessarily in a 1-year period was recorded. Based on the number recorded, a surgeon was identified as either prescribing unnecessary blood transfusions frequently. So this is the one we couldn't decide upon or put these folks in. This is like random. So if they were either they're described as frequent. They frequently gave unnecessary blood transfusions, occasionally did that, rarely, or never. The summary table of the resulting data is on the next slide. Are the attending physicians and residents in training distributed equally among the various unnecessary blood transfusion categories? In other words, are the population distributions of the unnecessary blood transfusions the same, or are they different for the attending and the residents? Okay. So here's our data. There's our two fixed values here. Our categorical variable is physician, or it really should be surgeon, really. Because these are surgeons, not physicians. And then there's the unnecessary blood transfusion frequency factor, all right, or category. All right, so we've got that. I won't bore you with putting this to R. We will just walk through the R procedure for this one. But notice that this one's got 4 rows and 2 columns. So we've got a 4x2 matrix that we're going to build in R. And again, we'll still go left to right, row by row, as we enter them in. And so the ho and the ha here, or the ho here is the population distributions of the unnecessary blood transfusions are the same among attending physicians and residents. Which would be good because somebody with more experience, if they were doing the same thing, then maybe there's not an issue. Versus the ha, the population distributions of unnecessary blood transfusions differs among attending physicians and residents, which may be a problem in how the training's going for these residents, right? Actually, the ho could be a problem too if you've got both parties doing the same thing. It means the folks who've had more experience are giving bad advice to the new kids on the block. Okay, so either one of those could be conceived bad depending on what your definition of unnecessary here is, and how harmful that really is. Okay, so we got the contingency table in the R. I called it blood mat. In my matrix function, I got my data in there going again left to right for each row. So 2 and 15 was the first row, 3, 28 was the second row, 31, 23 third row, 13, 5. And then I put my number of rows, my number of columns, and by row equals true in here. If you ever do this and this does not look like the table of data that was given to you, you need to do something and go back and retry to fix that so it looks exactly like that, because otherwise you might get different results than what you want, because you'll have data in places that won't be in the spots it's supposed to be in. So double check your data on these. Don't just willy-nilly run through these problems. Okay. Then I checked the chi-squared. Use the chi-square.test with the money expected after it to check my assumptions, and lo and behold, again, we still haven't run into one where there was an expected value less than 5. So check the assumption's good. We're good to go. That's what if I ask you to make a comment on that, that's what I want you to say. All the expected values are greater than 5. I feel comfortable proceeding with the chi-squared test of homogeneity. Step 4. We ran the actual chi-square test by eliminating that money expected argument at the end of the function, and it gave me a really freakishly small p-value. Not the smallest I've ever seen, but pretty dang small. It's hella small, as a matter of fact. But it ends up being 0.000005543 if you move the decimal over. So it's really damn small. All right, so we reject this in any universe and conclude the following. Since p is less than 0.001, we reject that hoe. There is very strong evidence, or there is hella strong evidence, if you want to put that in there. I'd make me laugh. I might give you a bonus point in these things. There is very strong evidence that the population distributions of unnecessary blood transfusions differs among attending patients, or attending physicians, not patients, and residents. We don't want patients giving their own blood transfusions. And so that's it. Guys, if you have any further questions about these two particular tests, please ask. The one thing I want to kind of note on here is that when I give these to you, like in an R project or the final exam project, I'm not going to tell you which one of these to run. You can see, as far as the R code's concerned, with the homogeneity and independence, you're going to run them similarly regardless. So those things won't be messed up. But how you write your hypotheses and your conclusions do depend on you knowing which test you're running. So I will give you clues in the problems, like for a chi-square test of chi-square goodness of fit test, for example. I have to give you the theoretical probabilities. I have to give you prescribed probabilities for you to compare your data to be able to do that particular test. So that's a dead giveaway that you're doing a chi-square goodness of fit test. If you're doing a chi-square test of independence, then probably most likely somewhere in that problem the word association between the two categorical variables has been mentioned, or the word independence or dependent has been used, or maybe the word related. All right, those are the kind of ways you can determine whether you're doing an independence test. If you're doing one for homogeneity, then it's usually talking about the population distributions of one group similar to or different from another, and that's kind of the dead giveaway that you're doing one versus the other one of those. So there's always going to be something that tells you. So when I ask you which type of test you're running and then ask you to tell me how you know that, I expect you to go, I'm running the test of homogeneity because we're trying to find the difference between the population if there's a difference in the population distributions between this group and this group. So be descriptive about those things, because I'm going to be picky about that stuff. I want to know that you know why you're running it. It's not just important to be able to run it. It's important to know why you would run it. I hope everybody's doing great. Again, reach out to me with any questions you have, and I will talk to you guys later.